Hey guys, welcome to another wonderful calculus lesson. Before we start, I have a very important question to ask you. So there it is. What would you do if you weren't afraid? Would you venture more guesses in my class? Would you be okay writing down an answer to a question if it might not be right? So I want you to think about that as we go through the rest of the lesson, okay? I'm going to have you guys start off. I want you to press pause and you are going to go through example 1 all on your own. Come up with answers for every single one of them. That's what I'm going to challenge you to do right now. And when you're done, come on back. So I'm going to give you 3 seconds to press pause right now. All right, there, by the wonderful magic of the powers that be, that is the graph of our function. And so that's part A, graphing it on the right. And you can see that I've shaded it from x equals 1 until x equals 4. So the first part is asking you to find f of x, the definite integral of f of x from 1 to 4 using geometry. So the shaded region is just a trapezoid. This would be, remember, a trapezoid, the area is 1/2 the height times the sum of the bases. And the height is always the distance between the two parallel sides. So this is actually our height. This distance would be base 1, and this distance in here would be base 2. So using geometry, we can go ahead and calculate the area of this. All right, so there's the formula with numbers plugged in. You'll notice that the h value is 3, and that's just the distance of the x equals 4 and the x equals 1. So this h distance is 3. That's where this number comes from. And then f of 1 is our first base, and f of 4 is our second base. And remember, this is the equation for f of x. So those are exact values. It's not like we're estimating them from the graph. Add it all up and you get a lovely number of 22.5. Part C asks you to find the definite integral using an antiderivative. So remember from our fundamental theorem of calculus, if you can evaluate a definite integral, all you have to do is find the antiderivative and then plug in the bounds and subtract. So I'm going to go ahead and show my work now. All right, so let's talk through the work just to make sure we're all on board. First thing I did is I substituted f of x, which was 3x, and that's my integrand. Now I can go ahead and find an antiderivative. The 3 is a constant, so that could technically stay to the front, and the antiderivative of x is x squared divided by 2. That's where this comes from. We mentioned in class there is no plus c on these because you're going to be evaluating these over specific numbers, so the c's are going to end up canceling. We're going to plug in the 4 first. So remember, this is the evaluation. So plug in the 4 and you get 4 squared, plug in the 1 for 1 squared, and lo and behold, you're going to get a value of 22.5 for that region. Okay, so compare your answers from B and C. What do you notice? They're the same. Yeah. Okay, now for part E, write an equation for a function in which you would not be able to use geometry to evaluate the integral. So I'm going to check this tomorrow in class, so have an answer for me on part E. I don't know why I'm stumbling on all my words. Bear with me. All right, for this next one, number 2, I want you to go ahead and evaluate this definite integral from x equals 1 to x equals 4 of the function x squared minus 5x plus 2. So go ahead and hit pause. I'm going to give you 3 seconds to hit pause right now, and then go ahead and do that definite integral. All right, for this one, I went ahead and showed the antiderivative, and I get a value, or an antiderivative. X squared is going to turn into x cubed divided by 3. A negative 5x becomes negative 5/2 x squared, and 2 is going to turn into 2x. All this is going to be evaluated from x equals 1 until x equals 4, and when you do this, you get negative 10.5. I'm going to show you in just a second all the work for that if you need to see it. So if you don't need to see it, you can skip over this next little part, but the work is going to be down below, and then I'm going to erase it after that. So hold tight 1 second, I'm going to put it up. All right, let me explain all this craziness that I've got going on here. First things first, when you evaluate a definite integral, you plug in the top bound first. So that's the first thing I did. Into that antiderivative, I plugged in the 4 in every location where there was an x. Now here's the biggest piece. You're subtracting the entire quantity with the 1 plugged in. So when you do that, you got to make sure you've got parentheses around this or you're going to miss distributing a negative. I never reduce or simplify fractions until after I combine the two quantities. So I've got orange representing the first quantity in each of them. So 4 cubed is 64, and I left that over 3. I didn't reduce it. I didn't worry about the fraction. Then I've got 1 cubed divided by 3, so that's the 1/3. So I put those guys in orange just so you can see. They're going to have the common denominator, so I can subtract them now. So 64 thirds minus 1/3, and that gives you 63 thirds. The next quantity was that x squared term. When you plug in the 4, 4 squared gives you 16. 16 times 5 is 80. And yes, I expect you to be able to multiply that, dumplings. When you plug in the 1, 1 squared times 5 halves is just the 5 halves. So that x squared term I've gone ahead and shown in purple. And then the third term of that antiderivative with the 4 plugged in becomes the 8. With the 1 plugged in becomes the 2. So again, the first term I've put in orange, the second term I've underlined in purple, and the third term I underlined in yellow. Now combine those same terms. The 64 thirds and the 1/3 became the 63 thirds. The negative 80 halves plus the positive 5 halves gives you negative 75 halves. And then the positive 8 and the negative 2 gives you the 6. 63 divided by 3 gives you 21. 75 divided by 2 gives you 37.5. And 6 is just 6. The 21 plus the 6 gives you 27. Take away 37.5, and there's the negative 10.5. Okay, so if you need to pause and absorb all this, go for it. We're going to go ahead and move back to B in just a second, so go ahead and hit pause if you need to. For part B of this problem, it says, use your calculator and sketch the graph of the integrand. Shade the region, and then you can use your calculator for this to get exact values of x. You can also just plug it in. I'm going to go ahead and show the graph in 1 second. Okay, so this time notice that the shaded region between the function and the x-axis is below the axis. So if you were to take a guess, definite integrals are what kind of areas? It's not just area, it's signed. S-I-G-N-E-D. Wow, yellow's kind of hard to see. How about that? Let's make that blue. Okay, so we're talking about signed area, meaning if it's above the axis, it's positive. Below the axis is going to be negative. Okay? All right, now for this example, we're going to explore what happens when our A value is actually larger than our B value. Remember, A is this term down here, and B is this term down here. So I want you to go ahead, find an antiderivative, and evaluate that definite integral. Do part B, where you use your calculator and you go ahead and sketch the graph of the integrand, shade the region, and we will come back and we'll discuss part C in class. But I want you to hit pause and go ahead and do A and B, and you'll see the answers in about 3 seconds. All right, there's the graph, and I apologize for the scale of it, but so for this one, you should have had a definite integral value of negative 16. Now the area is not below the x-axis. The area is above the x-axis. So I want you to think, why would we be getting a negative value? So go ahead and write down an answer for C, and we'll come back and touch on that in class. All right, we're going to take a look at what happens when you add integrals together that have the same integrand. So take a look at this graph right here. We have f of x is being graphed, and we've got on this first integrand, or on this first definite integral, we're starting at x equals a, and we're going until x equals b. Okay, so if I was to shade this region in, I would say that that's this area right in here. Okay, so that's what this little piece is going to find for us. And if we add that together with the second integrand, which is this little guy, and we are starting at B and going until C, what do you suppose this is going to equal? If I was to rewrite this as one integrand, what would the bounds be? Take a guess. It's okay, you can say it out loud. I don't care if people are listening to you. Well, the integrand is still f of x dx, and we're still starting at A, but since we're adding the two regions together, we can go ahead and just skip right over B and go straight to C. Were you right? All right, give yourself a high five. It's kind of hard to do. Well, it's not really hard to do, but you look really silly doing it, don't you? All right. Integrals between symmetric limits. If you know that the function is even versus odd. The AP exam loves to test your knowledge of functions to see if you can do things a little bit more quickly. Remember, we like to take shortcuts as human beings, so I'm going to teach you another little shortcut here, okay? Reminder of an even function. An even function is one that is symmetric about the y-axis. So this first graph here is symmetric over the y-axis, and if you pick a value of negative a, let's just say that's that guy, and you go until x equals a, okay? The idea here is if you know what this shaded region here is, okay, then the entire region is just going to be twice that. Okay, so this is just kind of one of the fun little properties that we can use. We could start at 0, we could go until x equals a, and it would be twice that value because you're basically accounting for the fact that it's symmetric. Okay, it's pretty straightforward. You'll see some functionality of this when we just take a look at some of those example problems, but the idea is fairly straightforward. Now, on the flip side, an odd function is one such that it has origin symmetry. And origin symmetry means that the function, when you go to a value, let's say we go to x equals a, this would be f of a. That's supposed to be an f. There we go. That would be f of a. Now, if you go in the opposite direction to a negative a value, an odd function has the feature that the y value is the exact same distance from the x-axis, but it's in the opposite direction. Okay? So this has the quality that it would be f of a, but it would be negative. Okay, so that's what an odd function is, to remind you guys of that. Now, if you take a look at the definite integral of this, and let's go ahead and shade this region, from x equals a negative a, this region here, to x equals positive a, okay, and remember what we just learned, if the function is below the axis, that area is considered negative. Okay, so basically on the left-hand side of this guy, we have a negative area. We can call that negative a. And then on the right side, we've got the exact same region, but it's positive. So this is everybody's absolute favorite feature in the world, where if you know that a function is odd, then the definite integral from negative a to a is just going to be 0. The areas basically cancel each other out. Okay? Yay! Now, it requires you to know something about functions and whether they're odd or even for those properties to make any sense at all and for them to even be useful. So if we go ahead and take a look at the first example, remember you can break up an integrand that's separated by addition and subtraction into lots of little integrands. So I'm going to show this. This is going to be a lot of work, and you do not have to do this for every time, but I want to be very clear the first time around. I could break that into all of these different integrands, different integrals, I should say, and negative 1 to 1 of 4 sine of x, and then I'm going to keep this thing going. We're going to say plus the integral from negative 1 to 1 of 3 dx. Okay. Now let's take a look at the very first integral. X to the 5th, that's an odd function. So if you look back at your previous page, this entire quantity, I'm going to change colors here so it's a little more obvious, this entire quantity is going to 0. Okay, it's an odd function. 6x cubed is also odd, so that one's done. 4 times the sine of x, that one's also odd. Okay, and the only reason it's not so much that the function's odd, but it's odd and we're going from -1 to 1. So we're using those symmetric bounds. Okay, and now for the next one, 3dx, that is not an odd function. That guy's even. Okay, so if you want to think about what does that look like, remember 3 is just a constant value. So if you were going to go 1, 2, 3, and you were to draw a line in there, okay, so we're basically going from -1 until 1. So we're finding this shaded region right in here. So this little region right in here. And it's up to you. I mean, this is just a rectangle. It's got a height of 3 and a width of 2. So 2 times 3, and we're getting a value of 6. It might be really funny if I was concentrating so hard and I said the wrong answer. Awkward. Okay, so all of that, we didn't have to find any antiderivatives. We just used our knowledge of functions, and we evaluated it as quickly as we could. So not too shabby. Take a look at problem number 2, and I'm going to go ahead and erase some of what I wrote. So if you didn't finish copying, go ahead and hit pause right now. There we go, that's better. Now, x to the -2 is 1 over x squared. And if you're not really sure what that looks like, you have to have, again, some knowledge of functions. That has a vertical asymptote at x equals 0. How come? Well, if you have x equals 0, you've got a 0 in the denominator, and I think we all remember that from first semester. 0 in the denominator means a vertical asymptote. All right, so I want you to think about this. If I'm trying to add up all the area between the function and the x-axis, can I do it? Is it allowed? This whole region in here. Whoa, it could have changed colors. Oh well. Okay, can you do that? Can you add up that area? I want you to come up with an answer for me and we'll talk about it tomorrow. Okay? And then the very last problem that we're going to do. So if you need to come up with an answer for 2, hit pause. I'm going to be checking you guys on this stuff, so don't just take shortcuts on this. Number 3, we've got a square root of x. And that graph looks like that. It's a sideways, top half of a sideways parabola. And we're trying to add up area from -2 until 2. Okay? So I want you to think about this definite integral. What does it mean to take that and add up the area from -2 to 2? Can we do it? Think about it. Come up with an answer for 2 and 3, and I'll talk to you guys tomorrow. Peace.